Hey, I'm Mack, and this is my lab report on the constant motion lab. We are showing that when there's no outside force acting on an object, it stays in constant velocity. This is known as the momentum principle or Newton's second law, and we're showing why this is the case. And in reality, this is basically never the case because there's almost always an outside force. So in this lab, we're only dealing with the position update formula. That is because, like I said, the outside force is 0, and for this same reason, v average is always, or the average velocity is always constant. So the only thing we really need to worry about is what the change in time was and initial position. And for our case, we picked the initial position, so that's going to be 0, making everything very easy. As I said, the outside force is 0, and so momentum is unchanged and it's just in the direction of velocity, as is always true, but is particularly true here because we're moving with constant velocity in one direction. Or well, velocity is a vector, so actually if it was a change in direction, velocity wouldn't be constant. So here is the experiment that I did. I simply rolled a skateboard across the room, well, kicked it. So when you kick it, you give it an initial velocity, and aside from that, there should be no extra force on the skateboard. In this specific example, the front wheel is the point that we are concerned with here. That's what I took my measurements off of. And it should be noted that obviously there's friction, wheel bearings aren't perfect, there's air, many things. So while the velocity isn't exactly constant, it's very close. And in fact, it was very close to 2 meters per second. As you can see here, I changed the ball velocity here to 2 meters per second. As well in the code, we made the change to where the ball position more accurately reflects the position update formula. Here in the comment beneath, you can see that the final position equals the initial position, which in this case is just the position from the previous loop through the while loop. And the ball velocity is constant, so all you do is multiply by the change in time, and you get the updated position. There should be a small difference here because this is perfect. You're just running through the while loop, updating the position with the exact velocity, and obviously a skateboard is imperfect. My room probably isn't even level. Here are our graphs. These are the two graphs that I pulled off Tracker and the code. So as you can see here on the coded one, it is a perfectly straight line. As well on the graph where we compared the two, they're perfectly straight. This makes sense because obviously it's just 2 meters per second. It's perfect, nothing to think about here. Here we see small differences, between the imprecision of my mouse click on the center of the wheel. It's blurry, my phone's old, the video's bad. But as you can see when we look at them on the same graph, they're very similar. They end in essentially the same spot, and aside from a few small errors which could be done with both my mouse and just a imperfectly smooth floor, it is very accurate. One thing to note here is that the time frame is very small. It's less than half a second. The error would build up over time, making it even more inaccurate, but I rolled the skateboard into my backpack, cutting it short so that the small forces in the other direction didn't have time to add up. With no outside forces acting on an object, it should move in constant velocity. This makes sense when we look at our equations. There's nothing weird going on. It should just happen as it does. Yeah.